This is a lecture on the electric field, in particular the electric field due to a collection of point charges. And by point charges I just mean a charge with no extent. It doesn't take up any region of space. So we'll start out by talking about an overview of the electric field, give its definition. Then we'll talk about how that definition implies basically an expression for the electric field due to one point charge. Then we'll mention that you have an electric force. So given a known electric field, there will be a force of that field on a point charge, and we call that the electric force on point charges. And then finally we'll do an example where we talk about the electric field at a point in space that is due to a collection of point charges using the stuff that we learned above. So let's start out with the electric field and its definition. We talked in a previous lecture about the electric force, or the Coulomb force, and the electric field is really just a generalization of that. So it's the force per unit charge at a point in space. And we find it by doing exactly that. So the electric field is defined to be the observed force on a test particle, so it's a test charge, divided by that test charge. So it's force per unit charge. So let's see what that means in practice. So this test charge is sort of your own tool. It's not a charge which the field depends on at all. It's just like a charge that you had in your pocket and that you bring out and hold up in a room here. Let's assume that your test charge is positive. So we'll just say that that's going to be greater than 0. The charge of that test charge is positive. And let's assume that you let it go and you observe that it accelerates. So maybe it accelerates off in this direction. So we'll just draw a little acceleration vector there. Let's also assume that this room is out in space. So there's no gravitational force, there are no other forces. So we know that that test charge is accelerating because there's an electric field in the room. And we know from Newton's second law that that acceleration must be due to a force. So we can draw that force. I won't draw it. We don't know exactly what the magnitude is because it depends on the mass of that test charge, but we know it points in exactly the same direction as the acceleration because of Newton's second law. And we can call that F of E on Q test. So there's a force due to some electric field, and then we figure out what that electric field is, and based on this equation here, the electric field is proportional to that force, but you divide off the test charge. So again, I don't know exactly what the length of it would be because it will depend on the value of my tool, of my test charge that I used, but I know that it points in exactly the same direction as these other vectors. So this is the electric field at this point in space here, this point. So the field does not depend on the test charge. As I said, it's your own tool. It's the thing that you keep in your pocket. So we could have actually done it the other way around. We could have taken a negative test charge if we wanted, and then we would have observed something different. We would have observed that the test charge would accelerate in the opposite direction. And if the test charge accelerated in the opposite direction, then that would mean that there's a force also in the opposite direction. But then when we go back to our equation, we would be dividing that force vector by the test charge, which we said now is negative, and that would flip this vector around to give us an electric field which is exactly the same thing here. So it does not matter what sort of test charge you use. It doesn't matter the magnitude or the sign of it. You'll always get exactly the same electric field. Now in practice you need to use a test charge that's small enough that it doesn't disturb the electric field, but we don't really need to worry about that right now. And also in practice, it's probably best to just simply assume that your test charge is positive, and then you don't have to do all that flipping around stuff that I talked about. So we should take a moment to talk about what we mean by the electric field, the field part in particular. And so if you're asked the question, what is the electric field in this room, we didn't really answer that question. All that we did was we answered what is the electric field vector at this point in the room. The electric field, what a field means, is a vector at every point. So if we were to actually be asked this question, we would have to go to every single point in the room and do exactly the same test. And at each of those points, we might find an electric field vector that points in a different way, and the collection of all those field vectors is what we call the electric field. So you must find a E vector at every point. So that's what it means to find a field. So it's quite a leap from what we've done in, for example, the first semester of this course, where we mostly talked about forces at a point, like the force on an object at a certain point. Now we're going to move to talking about fields, which are vectors at every point in space, and that complicates things a bit. Okay, so let's talk about the electric field of a single point charge. So we can use that definition above. I'm going to use this capital Q as my point charge. Generally, we use a capital Q or a lowercase q, either way. These are point charges, and if it's going to be a test charge, I'll say that. So this is just a point charge, but now it's an actual charge creating a source for an electric field. So let's try and determine what that electric field looks like based on what we know and based on the definition. So we can take a test charge. Well, first let's pick a point in space. Remember, we have to go to every point. And imagine, I'm not going to draw it this time, but imagine that I put a test charge there. Let's say that it's a positive test charge. And I guess I need to say that this source charge is either positive or negative. We'll assume a known source charge. So let's say that this is a positive source charge. So if I take my test charge and I place it here, and this is positive, then I know that a positive test charge will be repulsed by a positive source charge here. That's just Coulomb's law. So I know the force observed would be directly away. But because of my definition here, if the force observed is directly away, then the electric field should also be directly away. So I know that there should be an electric field vector at this point which points exactly away from my source charge. That's the electric field at that point. We could move to a different point in space, so let's say the same distance away, but over here maybe. Again, it's going to point exactly away, and it's going to have exactly the same magnitude because the magnitude of this is going to be determined by the force, and the force has a 1 over r squared in it. So as you get further and further away, the force gets smaller, and that means the electric field gets smaller because the force gets smaller. So this is the electric field at that point. If I move further away, so let's say that I moved to this point here, then my electric field would be smaller. In fact, it's going to drop off as 1 over r squared, as we said. So it points away, but it's smaller. And if I move closer, it's going to be bigger. So maybe it's going to be like this, something like that. Sorry, I didn't draw it so nice. So a closer point might have a larger electric field. So we see that the field points either towards or away from a positive or a negative source charge, respectively. If this was a negative charge, all these vectors would be pointing towards it. And then the field gets weaker, and that's because of the definition of the electric field and the fact that we know that for two charges, that force is just the Coulomb force, which drops off as 1 over r squared. Now, what about the magnitude of the electric field? So we can find that exactly. So let's do it. We can find it from the definition. So the definition says the electric field vector is the force vector divided by the test charge, but I can just take the magnitude of that equation. So the electric field magnitude is equal to the magnitude of the force of the electric field on the test charge divided by the absolute value of the test charge. In this case, it's not a mystery what this force is. In the case of a source charge, which is a point source, you're going to have a point source and a test charge, which are both point particles. So that force is actually just the Coulomb force. So this is our FQQ that we learned about as the electric force. And again, I still have the test charge, and this should actually be Q test up here. And the Coulomb force, we know exactly the expression for. We've done it before, so it's going to be K, and then we have absolute value of Q, absolute value of Q test, over r squared, the distance between them. And then we have absolute value of q test in the denominator. So what do we get? Well, the test charge drops out. As we said before, that electric field should not depend on the test charge. It's just your tool, and you're left with kq over r squared. Let me give myself a little bit of space for that. So we get an expression that is the magnitude of the electric field of a point charge. In fact, let's make it specific to that. Let's say that it's the electric field of a point source charge q is equal to k q, and we have to put an absolute value around it, over r squared, where r has exactly the same meaning that it did for the Coulomb force. So that's our expression for the magnitude of the electric field. So as a vector, the electric field of a single point charge, it points away or towards that source charge, depending on whether that source charge is positive or negative. And the magnitude of that vector is given by this equation here. And that's everything you need to know about the electric field vector. Now we can summarize that in sort of a neat way where we can show the electric field at all points in space. So as we said, the electric field is a vector at every point. So how do you do that? Well, you draw lines. So I'm going to take the two cases of positive and negative separately, and I'm going to draw these lines emanating away from the charges. In fact, I'll draw it for both. So these are two separate rooms isolated from each other. And then what you want is for these field lines to be everywhere parallel to the electric field vectors, and that's why I drew them like this. So the electric field vector at this point will point away, and I indicate that by drawing little arrows within the lines like this. So this picture is meant to show two things. It's meant to show that the electric field is pointing away wherever you see it. The electric field vector must be parallel. And the other thing is that as the field lines get further and further apart, that's an indication of the field getting weaker and weaker. The negative source charge will look almost exactly the same, except the electric field vectors should point towards that negative charge, and therefore the field looks like this. But again, it's strong here where the lines are close together, and it's weak out here. And that's really just a metaphor. So these things drop off as 1 over, the distance drops off as 1 over r, whereas in reality we know that the strength actually drops off as 1 over r squared. So if you were to draw this picture in 3 dimensions, then it would actually be correct. In 2 dimensions, it's really more of a metaphor. So one last thing before we do the example, and that is the force on a point charge due to an electric field. So basically what we can do is we can say, well, we know the definition of the electric field looks like this, but let's sort of invert it. Let's say that instead of having a little tool that is our test charge, let's assume that we know exactly what the electric field is, and that we have a real charge, a real point charge Q. And then we just rearrange this equation, and we get that the force of the electric field on the point charge Q is equal to the point charge times the electric field. So we can see what that looks like. So I don't need to restrict myself to the field of a point charge anymore. I can just say, imagine that somehow an electric field that looks like this is formed, and let's put little lines, little arrows on it to show the direction of the electric field. So again, what this means is if you went to this point, you would find an electric field vector which looks like this. If you went to this point, you would also find an electric field vector that's parallel, but because the lines are closer together, it should be a longer, stronger vector with a larger magnitude at that point there. But what if we put a test charge in there? So let's take a test, sorry, not a test charge, but a point charge. So we put some point charge there. What will happen to it? Well, if it's a positive charge, then you have a positive number multiplying the electric field vector. So that means the force will be in the same direction as the electric field. So we can draw, let me do it in black, the electric force on that test charge will be pointing somewhere like this. So this is the force of the electric field on the point charge. Sorry if I said test charge. We don't have a test charge here, it's just a point charge. If it's a negative charge, so if I put some capital Q less than 0 here, then we know that the electric field points right, but if you multiply the electric field by a negative charge, then that will flip the vector around so the force points in the opposite direction. So we have a force which is going to be pointing like this in that case. So this is the Fe on capital Q instead of the Fe on little q. Okay, so that's the force on an electric charge, and that's it's sort of one of our fundamental forces. The reason that this is more fundamental is because the electric field, it turns out, is the fundamental thing. So we're going to find that the electric and magnetic fields sort of interact in a way that they can be understood completely independently of forces. And then once you put charges in those fields, you'll see the forces acting on charges. So this is sort of how we made the transition from forces to electric fields. But at this point, we should really start to think about electric fields being their own thing. And that's why I could draw a picture like this. Okay, so now we'll move on to our example, and that will be the last part of the lecture. And that is to find the electric field at a point due to a dipole source. So a dipole simply means two charges which are oppositely charged but have the same magnitude of charge. So this is Q greater than 0, and then down here I have minus Q, so just the opposite of it. And I've shown that they're a distance d apart, and that this point P, the one point in space that I'm interested in finding the vector, is located a distance L from the line that connects the two charges. So how do we do this? Well, first, we should recognize that we're not being asked to find the electric field everywhere, only at a point. That's nice. That means our answer should just simply be a single vector. But the electric field, if you're asked to find the electric field is a vector, so your answer must be a vector. And that means that the techniques that you use to find the answer should be vector techniques. So we can write down the basic equation first, and that is that the electric field at point P is equal to the sum of the electric field due to the first charge plus the electric field due to the second charge. So this is a principle of superposition, which we saw back in the first semester of physics. So I'm just going to label these as Q1 and Q2 just to be specific about it. And the reason that the total electric field is equal to the sum of the electric field by each point charge is just because it comes from the force, and we know that forces add up in that way. So really this is going to look a lot like adding up forces within, for example, a Newton's second law problem. And the thing I'm going to do next is going to look a lot like a free body diagram. So let's look at that. So we need to find the total electric field. Maybe I should just say this is the electric field at point P, the total electric field at point P. And it's a vector equation, and so we're going to need to use vectors. So let's draw what it looks like. It's always best to draw it out first. So let me draw just a couple other lines on here. Let's draw the line that connects the points, the point charges to the point in space. And maybe I'll give that a name. We'll call this R1, and we'll call this R2. And we can draw the vectors because we know how it works now. So imagine that I place a test charge at point P. What would be the effect on that test charge due to the positive charge? Well, because the test charge I'm going to take out of my pocket is positive, and this is positive, there'll be repulsion. So we know that the field will point directly away because, oh geez, that's not right. Let me directly away, more like that. And we know that the field points directly away because the force would have pointed directly away. So the electric field due to the first charge is going to be pointing in that direction. And then take your test charge again, put it at point P, and imagine what would happen to it due to the second charge, due to this negative charge. Well, the negative charge will attract that positive test charge, and so therefore the electric field at this point must point exactly along the line, like that, and that will be our E2. So now we see our E1 and E2, and we can already see how it's going to start to work when we do this addition here. Before we do any of that, let's just calculate what these magnitudes should be. So what are the magnitudes of E1 and E2? So E1, magnitude E1, we have our equation from the 2 pages ago, which is that the magnitude should be equal to K, absolute value Q1, over R1 squared. Now, R1 is just this distance from the point charge to the point in space, and so that's going to be equal to, I guess, the square root of L squared plus D squared. Let's just call that R. And the reason I'm calling it R is because this thing will be exactly the same, as you can see from the bottom triangle. So another thing we can say is that Q1 can just be called Q, because we said that Q1 is a positive charge, and Q2 is just a negative charge, and each of them have an absolute value of just Q. So this is KQ, I guess I should say, K absolute value Q over R squared. So that's the magnitude of the first field vector. The second field vector, as I've almost said already, is exactly the same. It's KQ2 absolute value over R2 squared, but again, these are KQ R squared. So E2 is equal to E1 in magnitudes, and we could just call that like EQ, just to make something brief. So they each have the same magnitude, and they're going to be given by that. Now, as I said, we have a vector equation. So a vector equation can be dealt with in general in 2 ways. You can deal with it in a graphical manner, or you can deal with it in an algebraic manner, and let's do both. So let's take both cases separately. So let's say that we have graphical first, and then we'll do algebraic second. So the graphical method, what I mean is, you could just add up these vectors. We know how to add up vectors. I usually do it on a coordinate system. So let's take a coordinate system here, and I'm just going to take each of these vectors, so each one in turn, and drag it over to my coordinate system. So it looks sort of like I have this vector here. That's E1. And then I take the second vector, and I put its tail at the head of the first, and that's going to give me E2. And because they have the same magnitude, and because they have the same angle with respect to the horizontal, so this is some theta here, I know that it will end up exactly along this vertical axis, and that the total electric field vector, the resultant in this case, because of our vector equation, will look like this. So that's our electric field vector. So I'm not going to do it, but you can imagine that you could find the triangle here. So we have a triangle that looks sort of like this, where we have let's call it EQ. We have EQ here, that's the magnitude of the two. We have theta here, and then we have the total E that we're looking for, like that. And that will solve our problem. You can do a little trigonometry here. To find the vector, you already know based on this picture that it points down. And then you can find its magnitude by finding, for example, this side of this triangle, and then you double it to get the value of the magnitude there. So that's the graphical method. The algebraic method is we just, let me rewrite the equation. Our equation we're trying to solve is E vector is equal to E1 vector plus E2 vector. And as a vector equation, we have to break it up into components. So again, I'll take a coordinate system, x and y, and let's look at the x component first. So I'm going to be looking for the x component of the total field vector, and that's going to be E1x plus E2x. And I have to find those components. So I look at first this E1 vector, I place it on my coordinate system. Here's E1. I project back to the x-axis, and this number is E1x. And it looks to me like this is theta, the theta that we were looking at in that picture. So then my E1x is going to be equal to the magnitude E1, which we said was just EQ, and times cosine of theta. And it's a positive component there. The other one is going to look like this, E2 vector, and it's going to be projected back to this point. This is E2x. You can see that that's a negative number, but in fact it's going to be exactly the same negative number, because what is this going to be? It's going to be minus EQ cosine theta, so EX is equal to 0. So we found one component, and notice that exactly agrees with our graphical method over there. Now we do the y equation. EY, you want to be looking back up here at the vector equation, just rewriting it exactly, except putting in components. So EY is equal to E1y plus E2y. And then we find them. So E1y, we project back to the y-axis and get to this number. And you can see that that's going to be a negative number. It's going to be minus EQ sine theta. And E2y is going to be the same, also minus EQ sine theta. So EY is equal to minus 2 EQ sine theta. The E vector is going to be 0, comma, minus 2 EQ sine theta. And then we need to say what we mean by EQ. We already found it up above. EQ is equal to KQ over R squared. KQ, absolute value, over R squared, but R squared wasn't given, so it's going to be KQ over D squared plus L squared. And then we're done. Notice I didn't give you any numbers. You don't need numbers until right now. At this point, you could plug in some numbers to figure out what this value is, and then you could plug that in. Okay, that ends this lecture on the electric